Good morning and thanks very much for joining me. My name is Dominic Vella and I'm a Professor of Applied Maths at the Mathematical Institute in the University of Oxford, and I'm also a Tutorial Fellow in Applied Maths at Lincoln College, one of the colleges in the University of Oxford. Today I'd like to describe a little bit to you about what Applied Maths is, and I'd like to give you an idea about what studying Applied Maths at university would mean. So to answer the question of what is Applied Maths, I'd like to start off by talking a little bit about what applied mathematicians do. And in short, the basic answer to that is that we develop and then solve mathematical models of real-world problems. Now, historically, that's often focused on examples from the real world. So there's been a lot of work in applied maths on how fluids flow. And just as an example of that, I'd like to show you a time-lapse movie that you might see every day when you pour juice for your breakfast, or at some other time later in the evening some beer. And when you pour a glass of orange juice pour juice into a glass, then what you see is that the bubbles that form on the surface are not static. What they do instead is they move around and gradually they come together, and ultimately they tend to end up at the edge of the glass. And so I've been interested in understanding why that happens and how fast it happens. Now, other colleagues are interested in how we deal with data, large amounts of data. And in that class of problems, one sort of easily understandable example is trying to understand how we deal with images and how we compress images. A sort of similar issue is how we restore images that were formed using old-fashioned techniques, maybe with negatives and then forming photographic prints. And those prints tend to end up being damaged with creases formed or scratches on the surface. And there are a whole series of mathematical algorithms that allow you to sort of smooth out those issues and restore the picture to something close to what it looked like originally. Now, of course, with the pandemic going on at the moment, a lot of applied mathematicians are working very hard to try and understand how the pandemic is progressing and what kind of strategies we should adopt as a country and as a world to overcome it. And one of the key questions that you may have heard addressed in the news is this uncertainty over what the reproduction number R0 is. That's the average number of people infected by a single person. And one of the key uncertainties really is that this reproduction number is expected to evolve as we change our behaviour. And in particular, we'd like to understand how that reproduction number evolves in response to measures such as social distancing and the lockdown. And that's something that Robin Thompson here at the Mathematical Institute in Christchurch has worked on. This graph is not taken from COVID-19. Actually, this is data from an H1N1 outbreak back in 2009. So if that's what applied mathematicians do, then the question then arises of, well, how do they actually do that? And I'm going to try and show you some examples of that. But what these examples all have in common is that we start from a fundamental principle and then we write that principle down in maths and try to see what the logical consequences of the principle are. And perhaps the best example of one of those principles that I think many of you would have seen at school is Newton's second law. So you may have heard of it as F equals ma. That means that the forces on a body, F, is equal to the mass of that body times its acceleration, a. And if you've seen a little bit of calculus, then you might know that the acceleration of a body is the second derivative of its position with time, or the rate of change of its velocity. Now, an example of the use of Newton's second law that you also may have seen at school is to understand how a simple pendulum oscillates. So what I'm thinking of here is a pendulum with some length L, with a mass m stuck on the end of it. And what we want to do is to apply Newton's second law, so we need to think about what the forces on that mass are. Now, there's a tension from the string that sort of pulls it perpendicular to the direction of motion, but the sort of simplest way of dealing with the problem is to think about the motion the force is tangential to the motion, and in that case the force is just minus the weight mg times the sine of this angle theta. Now that force has to be equal to the mass times the acceleration, so I write the mass m, and then I write the acceleration, which in this case is the length of the pendulum times the second derivative of theta with respect to time. Now what you can see there is that I've got an equation for how theta will change with time, and what I'd like to start off by doing is thinking about what the solution of that equation looks like. the common approximation to make some progress with solving this equation is actually to assume that the angle theta is very small. And in that case, then you can say that sine theta is approximately equal to theta. So that this equation becomes much simpler. It becomes just the second derivative of theta with respect to time is equal to minus some omega squared times theta. Okay. Now this omega, you'll see, doesn't depend on the mass of the object, and I'll come back to that in just a second. But it's what turns out to be called the frequency. Now, if you've seen calculus and you've seen the calculus of trigonometric functions, then you may know that the function whose second derivative is minus itself are the trigonometric functions cos and sine. If you've also seen simple harmonic motion, then you may hopefully recognise this equation as being the equation of simple harmonic motion. But in any case, the general solution of this equation is that theta is some amplitude a times cos of omega t plus a phase phi. And because you know that cos wiggles up and down as time evolves, we get what we expected, which is that theta will go back and forth in time. The pendulum will oscillate back and forth. But the key thing is that this oscillation happens with a frequency omega that depends on the square root of the gravitational acceleration and the length of the string. And I think the first time that you see this formula, I think it's surprising that it does not depend on either the mass of the object or the amplitude. And just to convince you that that's the case, I took my two daughters to the park well before lockdown, and at that time the mass of the younger one was around 10 kilos and the mass of the older one was about 20 kilos, and so I put them both on swings next to each other, lifted them up and let them go, and what you see is that they do indeed have the same frequency. So then the question is, well, if we want to vary the frequency of oscillation of a pendulum, we could imagine perhaps changing g by doing this experiment on the moon or Mars or somewhere else. But a much simpler way of changing the frequency has to be to change the length of the pendulum. Unfortunately, there's a very nice demonstration of this on YouTube by the Harvard Natural Sciences demo, where they take a whole series of pendula of very different lengths and then they release them all at the same time. And I'm just going to show you that movie because I think the motion is quite hypnotic, or primarily because the motion is quite hypnotic. It turns out that actually they've chosen the lengths of these strings to be such that if you watch this movie for long enough, I'm going to stop it in a second, but if you watch this movie for long enough, then actually the motion turns out to be periodic and the pendulum starts swinging in phase briefly again, and the motion repeats. But the real reason I show you this movie is because it introduces this idea that while a single pendulum might vary just as a function of time, actually there's a class of problems in which things vary both in space and time. So you have two things varying and you want two independent variables, and you want to understand how a dependent variable depends on those two independent variables. And loosely speaking, that's really what a lot of applied maths at university is about. It's about how do we take the tools that you understand from school, where you deal with functions of one variable, and extend that to functions of more than one variable. So we might have a function f that depends on space and time, or we might have a function g that depends on two space dimensions or more space dimensions. Now, one of the key issues that you deal with very early on in your university mathematics course is how we talk about changes of these functions with respect to the different variables. And while at school you might have seen the d by dt to denote the derivative with respect to a single variable t, when we think about multiple variables we have to use a different notation. That's this curly d by dt. Okay, so once we've done that, then actually that sort of explains a little bit about what two of the core first year courses are all about. The first is Introductory Calculus, which you see in your first term of university, and it's really about trying to understand properly what the difference between the curly d by dt is and the straight d by dt. And there's a second course in the second term of your university career, which sort of looks at how we do integration in multiple variables. How do we undo partial differentiation as curly d by dt. Okay, so I don't want to talk too much more about notation. I want to get on and talk about the different behaviours that we see in equations in your university applied maths. And it turns out that there are essentially three equations that one can write down. The first is what's called the wave equation. It has two derivatives with respect to time on the left-hand side, and then two derivatives with respect to x on the right-hand side, and then there's a wave speed c. And this wave equation often comes from situations that use Newton's second law. So you can see that this left-hand side term looks a little bit like the acceleration that we saw in the pendulum case. And then the term on the right-hand side turns out to be related to the force. So if you're thinking about a string on a guitar being plucked, then the force depends on the shape of the string, and that's why you end up with these second derivatives. The second equation that comes up a lot is what's called the diffusion equation. And again, that looks like the wave equation, but instead of having an acceleration term on the left-hand side, it has only one derivative with respect to time. And we'll see why that's important later on. The third and final class of equations is what's called Laplace's equation. And again, that looks a little bit like the wave equation, but now it's got two spatial variables. That's not an important difference. The important difference is that rather than having the two derivatives being equal to each other, it's their sum that is equal to 0. And again, that has an important qualitative difference in the way that this function g will behave. Now, there's another course in the first year called Fourier Series and Partial Differential Equations, where we teach you some techniques for solving these three equations. And obviously I can't go into detail about that today, so what I thought I'd do instead is to talk to you a little bit about how the solutions of each of these equations behave, and to give you a little bit of a sense of why they're really sort of qualitatively different. Okay, so the first equation I'd like to think about is the wave equation, and as I said already, the physical principle underlying the wave equation is really Newton's second law. Now, the general solution of the wave equation is that it's some function of x minus ct plus a different function g of x plus ct. If you know how to, if you're happy sort of differentiating, maybe you can convince yourselves that this general function does indeed satisfy the wave equation. If you're not happy with that, then maybe you can see that this left-hand part, the big F of x minus ct, corresponds to a wave moving to the right. Whenever we do f of x minus something, that corresponds to moving the graph of big F to the right by some amount, and the amount that we're moving it to the right by is c times time. So it's kind of moving at a constant speed to the right. In the same way, the graph of g is moving to the left at a constant speed, c. So what can we do with a solution like that? Well, once you've done enough sort of physics to get you to a place where you can understand where this equation comes from, then you'll see that this wave equation actually describes how sound waves propagate. And a key case in which sound waves may come into your everyday life is when you're playing music and some of that music is going through the wall of your bedroom and annoying your parents. So the question that you might be interested in asking is trying to understand a little bit about why they always complain about how your music has too much bass and no tune. And really the answer to that question comes from a calculation that you can do in the third year Waves and Compressible Flow course, where you calculate how much is transmitted compared to how much is reflected as a function of the frequency of the waves. And it turns out that the ratio of transmitted to reflected sound scales inversely with the frequency omega. And that means that higher frequencies, where this omega is larger, t over r is small, so very little is transmitted, whereas with lower frequencies, the bass notes of your music, 1 over omega is large, and so much more is transmitted, explaining why the music that your parents hear is very bass heavy. Now, there are other solutions of the wave equation, and these come about from thinking about things like drums. These are what are called normal modes. They're waves that have, or solutions of the wave equation that have a perfect frequency. And so you can imagine having a circular drum and then hitting it, and we might expect the surface of the drum to form this sort of parabola shape, okay? And it turns out that that's right. That's the lowest frequency mode of the wave equation for a drum. But it also turns out that there are other ways that the skin of a drum can vibrate, and those are called the other modes, okay? So the second mode has this sort of hat shape, and then higher modes have more oscillations in the radial direction. And each of these different shapes has a different frequency associated with it. Now, unfortunately, you're not able to come to the Mathematical Institute today, but had you been there, you would have been able to see an example of one of these normal modes or eigenfunctions of the wave equation, which we have in a sort of atrium, glass covering an atrium in our building. Now, as I said already, each mode has its own frequency, and it turns out that frequency depends on the shape of the boundary. And in general, when one hits a drum, it turns out that we mix these different modes, the modes with different frequencies, and we end up getting a spectrum of different frequencies. And it turns out that actually how you hit the drum determines what the mix of those frequencies is and what the mix of those modes is. So you might find it a bit surprising that the way in which you hit something can change the sound that it makes. And if that's the case, then a simple demonstration you can do is to just take a mug and then to hit it either with a beater like I've got here or with a teaspoon in two different places. One of them is to hit it in a rim just near where the handle is, and that gives you this sound. Okay, but if you hit it 45 degrees away from there, you can hear that it's a tiny bit higher. Okay, and the reason for that is, of course, the mug is not perfectly symmetrical, and so where the handle is in comparison to where I'm hitting produces different modes and thereby different frequency or different sounds. Okay, so with that idea of how the shape of things can influence the sound, what I did is a quick experiment at home where I took a circular plate and I hit that in the center and I look at which frequencies are excited. I listened to the sound, and then with my iPad I made a graph of the spectrum. So this is decibels on the y-axis and then frequency on the x-axis, and you can see that there are some peaks that are associated with particular frequencies. Now, fortunately, my older daughter has also made a different shaped plate. Okay, so we also have a star-shaped plate with roughly the same size and thickness and so on, and the spectrum of that is very different. It has, again, a series of peaks, but you can see that they're all, or at least in this case, they seem to be quite equally spaced and not so far apart as they are in a circular case. So again, we don't have time to go into the details of this, but the important thing is that the shape of the plate makes a difference in what the sound is and what the quality of that sound is. And then to a mathematician, and maybe a natural question is to ask, well, if I listen to the sound of a drum or a plate, then could I work out from listening to what frequencies are in that sound, can I work out what the shape of that drum is? So you might phrase that question as being, can you hear the shape of the drum? And it turns out that actually the answer is no, although it took around 30 years to realise that, and the way that it was done was by finding a counterexample of two drum shapes that are different but have exactly the same sound when you hit them. They have exactly the same pattern of peaks in their spectrum. Okay, so there are many other examples of waves. I don't have much time to go into them, but the key thing is that while the differences, the sort of way in which those wave equations are derived may differ, the behaviour is often very similar. So this, I'm just showing you a movie from the SXS project, which looked at gravitational waves produced by two black holes colliding. Remember, this was a big thing at the end of 2015. When the first gravitational waves were detected. And this is a simulation they did of two black holes colliding, and it's really looking at the background field, and what you see in the second the movie will just zoom out after the moment of merger, and what you'll see in this far field is the gravitational waves propagating out. Now, of course, the differences there are there are many differences between this and the wave equation that I've talked about before, but the character of propagating waves is very similar. A second example is what's called the phantom traffic jam, and you may experience that when you're travelling on the motorway and all of the cars suddenly come to a standstill and then they all start up again without there being an accident or someone broken down. And the BBC One show did a nice demonstration of this a few years ago where they asked drivers to drive in a circle at a constant speed of around 10 miles an hour, and despite that same instruction being given to everyone, what you see is actually that very quickly, small imperfections end up causing a traffic jam that kind of propagates backwards all the way around the circle. Okay, so again, the details are different, but the phenomenology of a wave propagating is the same. Now I want to move on to talk about the diffusion equation, And here, this is an example that's a different physical principle than Newton's second law. So I thought it would make sense to talk a little bit about what that physical principle is. So in the situation of the diffusion equation, what we often think about is a metal bar that's being heated at one end. And what we'd like to do is to try and understand how the temperature in the metal bar varies with time. So what we do is we think about a very thin slice of that bar with width delta x, and we think about what the heat energy in that bar, in that segment of the bar is. Depending on how much physics you know, you might know that that heat energy, or the change in heat energy in a small time interval delta t, is the density times the specific heat capacity times the cross-sectional area times the width. So that's just the volume or the mass times the specific heat capacity times the difference in temperature, the change in temperature. Now the temperature in that bit of the bar can only change if a different amount of heat enters from the left than leaves from the right. Okay, so the change in temperature has to be related to the difference in this flow of heat, Q. So we have now an equation, but we don't know what Q, that I've written down, what's called the heat flux is. And here we have to use what's called Fourier's law, which says that the heat flows from hot to cold, or in mathematics, the Q, the heat flux, is some constant minus some constant times the gradient of the temperature, dt by dx. And if you substitute this expression for Q into here, and then take the limit of delta x tending to 0 and delta t tending to 0, then you end up with exactly the heat equation, or the diffusion equation. Okay, so as I've sort of indicated a little bit by my small slip there, the diffusion equation is often called the heat equation because it describes the flow of heat. And to give you an illustration of the kind of behaviour that the solution of the diffusion or heat equation has, it's very helpful to think about how things cook. So I'm going to show you an example taken from my favourite brownie recipe, which makes very good brownies. But what I think is interesting about this recipe is that the very first instruction in the recipe is that you should lightly grease a 20 centimetre / 8 inch shallow square cake tin. Okay. So the question is, well, I expect the recipe to tell me how much flour I'm going to need, how much chocolate, how many eggs, and so on. But the question is, well, why does it tell me what size tin I should use? And the problem that's exercised us in this house is, what should we do if we only have a 15 centimetre cake tin? How should we modify the recipe? I'm not satisfied with just making less brownie. I want to know how I should change the cooking instructions. Now, to a mathematician, the cooking of a brownie is very nice because it's quite a thin slab of cake. And so what you essentially do is you mix everything together, you put it in the oven, and then it's a thin slab that's being heated on the top and the bottom, and the mixture starts off cold, or at least at room temperature. And so what we say is that as a first approximation, the time taken to cook the brownie is going to be determined by how long it takes for the middle to get sufficiently hot that the egg and other bits get cooked. Okay? So what we're going to do is we're going to assume that brownies are a thin slab. The only dependence is in the y direction here. That cooking time is how long it takes to heat up the middle. And then we're going to assume that this diffusion coefficient d that comes up in the diffusion equation is independent of the thickness or anything else we're doing. It just depends on what material there is. Now, as I said already, I don't have time to talk to you about what the solution of the diffusion equation looks like. But what I want to do is to hopefully use a bit of intuition that this time derivative on the left-hand side looks a little bit like the temperature divided by the time it takes to cook. And on the right-hand side, I've basically got some constant d, again times the temperature, and then two derivatives with respect to y. Well, that's a little bit like dividing by the thickness h twice. So from this, I can kind of cancel out my t's, and I can end up saying that the time taken to cook has to be proportional to the square of the thickness divided by the diffusion coefficient d. And that's a really important result because, okay, it shows that the cooking time is proportional to the square of the thickness of the brownies, and that's quite a sensitive dependence. But also thinking about, get back to our brownie recipe, the recipe fixes how much volume of brownie mix we're going to make. So when I change the area of the tin, I'm going to change the thickness, and then hence I'm going to change the cooking time. So it turns out that when you do the calculation, just this very fact of using a 15 centimetre rather than a 20 centimetre tin means that the cooking time has to be 3 times longer. You make the thickness just that little bit bigger because the area is smaller, and so the cooking time goes up a lot. Now, of course, there are many more important and substantial problems that we can use the diffusion equation for than just cooking brownies. And one of the problems that a lot of my colleagues in mathematical biology look at here is how patterns form in diffusion equations. It turns out that if you have 2 chemicals diffusing with some interaction between the species 1 and species 2, then actually you can get some interesting patterns forming. And again, an interesting thing there is that the pattern that forms depends on the shape or the aspect ratio of the boundary. So I'm going to show you a movie in a second where we solve these pair of equations on a rectangular domain and on a square domain. And what you see is actually that the pattern that forms is very different. In the narrow rectangular domain, you end up with a series of stripes, whereas in the square domain, you tend to end up with spots. And the details of this are well understood at a sort of conceptual level, but it's also quite remarkable that these patterns depend on the geometry of the shape. And so it's been suggested that actually this might be partly the reason behind why many big cats have tails that tend to have stripes on them, whereas their bodies, which are closer to the square, tend to have spots. And again, some of the details of how this patterning in animal coats works is being worked out by researchers at Oxford at the moment. This patterning in general is something that's covered in 3rd and 4th year courses on pattern formation and mathematical biology. Okay, so the final equation I want to talk a little bit about is Laplace's equation. And it turns out that Laplace's equation describes a whole bunch of different phenomena. It describes the electric fields between charges, it describes flow of air past aircraft wings, and it also describes how things dry. But the key character of Laplace's equation that I want to sort of bring your attention to is the fact that it really doesn't like corners. Okay, so you might know that again from physics, that when you have a curved conductor or a highly curved conductor, charge tends to accumulate there, and that's the reason why buildings like the Eiffel Tower end up being struck by lightning a lot, because at the point a lot of charge accumulates. But that same disdain for highly curved regions or the onset of singularities near there is familiar in lots of other examples. It's also the reason why when you dry a drop of coffee, actually what you end up with is not a uniform brown stain on your worktop, but actually a darker ring stain with a more faded central region. And again, thinking about food, then when you cook potato wedges, what you tend to get is a very brown edge. Again, the evaporation is much faster at that sharp corner, and so the sharp edge tends to get hotter and hence to burn a little bit more. Okay, so I've given you a sense of the behaviour of these 3 equations, but thinking in this way is not the only way that we can do this. We can of course solve these equations on computers, and the key thing is really to do this in an intelligent way, and that's the subject that's called numerical analysis. And there are a number of courses in the undergraduate degree that talk about this. The first one is in the 2nd year. It's an optional course where you think about how to deal with matrices and how to represent continuous functions on a computer that can only handle the behaviour of those functions at a finite number of points. And then in the 3rd year, you would go on to study a little bit more detail how the solution of the diffusion equation and Laplace's equation can be found numerically. So I hope that I've given you a bit of a perspective of why I think it's interesting to study applied maths. I hope I've given you a bit of a new perspective on the world around you, whether it's thinking about how you cook brownies or how you cook potato wedges. There are many more examples, such as the wake behind ships in the sea that you would cover in the undergraduate degree. But that's not the only benefit of studying applied maths. I think it's also great that we can combine some of the best bits of maths and science. We can be helpful, provide solutions to real world problems, but we also get to make the kind of abstractions that mathematicians like to make, so that we can make as much progress as possible. But of course it doesn't end at university either. Going into the future and thinking about careers is important, and students that I've taught have gone into a whole range of careers in the past, from finance to software engineering, code breaking, teaching, and so on. So there's really a whole gamut of careers waiting for you once you have a degree in mathematics. So I'd like to finish there, but if you're interested in finding a little bit more out about applied maths in the spirit of the talk that I've given here, then I'd recommend this book to you. It's one of the Oxford University Press books called Applied Mathematics, A Very Short Introduction. As I said, it has some examples in the same spirit of what I've talked about today, but many more of them. And it's written by Alan Gorielli, who's a very good friend and also partly my boss. So with that, I'd like to thank you for your attention.